Imagine a process that generates so much heat it can melt steel. Now imagine harnessing that heat to fuse metal together. That, in essence, is the magic of aluminum thermite welding. This isn't your everyday welding technique. It's a process that evokes images of fiery reactions and molten metal flowing like lava. Intrigued? Let's delve deeper into the fascinating world of thermite welding. Have you ever wondered how railroads connect those massive steel rails? Or how ships get repaired at sea without needing a dry dock? The answer, in many cases, is aluminum thermite welding. This powerful process uses an exothermic reaction to create molten metal that fuses materials together with incredible strength. It's a process that's both fascinating and essential in various industries. Thermite welding uses heat from a chemical reaction to join metals. Unlike traditional welding, it generates heat through an exothermic reaction. The process involves aluminum powder and iron oxide, or rust. When ignited, a powerful reaction occurs. Magnesium is used to start the reaction. The aluminum rapidly oxidizes, combining with the metal oxide. This releases immense heat, over 4,000 degrees Fahrenheit. The molten metal flows into a mold, joining the metals. As it cools, it solidifies, creating a strong weld. The secret behind thermite welding's power lies in the principles of chemistry and thermodynamics. At its core, the process leverages the concept of exothermic reactions, chemical reactions that release energy in the form of heat. In the case of thermite welding, the reaction between aluminum and iron oxide is highly exothermic. Aluminum, a highly reactive metal, possesses a strong affinity for oxygen. When mixed with iron oxide, which readily gives up its oxygen, conditions are ripe for a vigorous reaction. Upon ignition, the aluminum atoms eagerly snatch oxygen atoms from the iron oxide, forming aluminum oxide and releasing a tremendous amount of heat in the process. This heat is the driving force behind the welding process. The molten iron, a product of this reaction, then acts as the filler material, fusing the metals to be joined. The intense heat and robust weld produced by thermite welding make it ideal for a wide range of applications, particularly in heavy-duty industries where strength and durability are paramount. One of the most well-known applications is in railroad construction and maintenance. Thermite welding is used to join the ends of steel rails together, creating a seamless track that can withstand the immense weight and stress of trains passing over them. This method ensures a smooth ride and reduces the need for frequent maintenance. Beyond railroads, thermite welding finds use in various other industries. Shipbuilding utilizes this process for repairing large vessels, especially in critical areas like the hull. The ability to weld underwater makes it invaluable for emergency repairs at sea. The process also finds application in the manufacturing of heavy machinery, pipelines, and even electrical connections for grounding systems. Its versatility and ability to join dissimilar metals, such as steel and copper, further expand its potential applications. Section 5. Safety first. Handling the heat. While incredibly useful, thermite welding is not without its risks. The extreme temperatures involved demand utmost caution and adherence to strict safety protocols. Handling molten metal at thousands of degrees is inherently dangerous, and even a small mistake can have severe consequences. Therefore, only trained and certified professionals should perform thermite welding. Safety gear is paramount when dealing with thermite welding. Welders must wear specialized protective clothing, including heat-resistant gloves, aprons, and face shields. The intense light emitted during the reaction necessitates eye protection with welding helmets equipped with appropriate filters. The work area must also be properly ventilated to prevent the buildup of fumes and ensure adequate airflow. A designated fire watch is also crucial to monitor the process and address any unexpected flare-ups. Safety training should encompass not just the welding procedure itself, but also emergency response protocols in case of accidents. Section 6. Advantages of thermite welding. Strength, portability, versatility. The unique advantages of thermite welding make it indispensable. One primary advantage is the exceptional strength of the weld. The molten metal forms a metallurgical bond, creating a joint often stronger than the surrounding material. This strength is ideal for high stress, impact, or vibration applications. Another key advantage is its portability. Thermite welding is self-contained, needing no external power. This makes it valuable for field repairs, underwater applications, and remote locations. Section 7. The future of thermite welding. Innovations and advancements. While a well-established process, thermite welding is not without its limitations. The intense heat generated can sometimes affect the surrounding metal, potentially altering its properties. Additionally, the process is generally limited to joining thicker sections of metal due to the high heat input. However, ongoing research and development are focused on addressing these limitations and enhancing the capabilities of thermite welding. One area of innovation is the development of new thermite compositions tailored for specific applications. By adjusting the proportions of aluminum and metal oxides, researchers can fine-tune the heat output and properties of the weld metal. Another area of focus is improving process control and automation. This includes developing more precise ignition systems and automated feeding mechanisms for the thermite mixture, leading to more consistent and repeatable welds. Furthermore, researchers are exploring ways to mitigate the heat-affected zone, potentially expanding the application of thermite welding to thinner and more delicate metal components. Section 8. Conclusion. The enduring power of thermite welding. From its humble beginnings to its modern-day applications, thermite welding has played a pivotal role in shaping our world. Its ability to generate intense heat through a self-sustaining chemical reaction, coupled with the strength and durability of the weld it produces, makes it an invaluable tool in industries ranging from transportation to manufacturing. While safety considerations are paramount, the advantages offered by thermite welding ensure its continued relevance in the years to come. As technology advances, we can expect further innovations and refinements in thermite welding processes, expanding its applications and solidifying its position as a powerful tool for joining metals. The next time you see a railroad track, a towering bridge, or a massive ship, remember the hidden power of thermite welding that holds these structures together, silently and reliably. Section 9. Glossary of terms. Exothermic reaction. A chemical reaction that releases energy in the form of heat. Metal oxide. A chemical compound containing a metal and oxygen. Thermite. A pyrotechnic composition of a metal powder, often aluminum, and a metal oxide, commonly iron oxide. Molten metal. Metal that has been heated to a temperature above its melting point and has become liquid. Heat-affected zone. The area of base material that is not melted but experiences changes in its microstructure and properties due to the heat of welding. Section 10. Further reading. AWS Welding Handbook, Volume 2. This comprehensive handbook provides in-depth information on various welding processes, including thermite welding. The American Welding Society, AWS. The AWS website offers a wealth of resources on welding, including safety guidelines, industry standards, and educational materials. ASM International. ASM International is a professional organization dedicated to the advancement of materials science and engineering. Their website provides access to technical publications and resources on various materials and processes, including welding.